Hopefully when it settles down, everyone will be able to hear me. I work in Dr. Cleveland's group as a researcher. I'm a second-year PhD student, third year next semester. What I do is I work with the technologies that have enabled the sort of data analysis that you're going to see more of. I've been asked to talk to you today about Hadoop, which is an open source product that we use here, R, which at least half of you raised your hand and said you had heard of before, and RIPE, which is a technology we use to bridge the gap between Hadoop and R and make them interoperable. I will not be talking about RIPE examples today. That's going to come at a later date. Hopefully this will take about 50 minutes. So earlier, Dr. Cleveland asked you, who's worked with Hadoop? And only like 3 people raised their hands. And I'm not surprised by that because Hadoop takes a little bit of infrastructure. My question is, who's heard of Hadoop before Dr. Cleveland mentioned it? Ah, there we go. Now that makes more sense. If you haven't heard of Hadoop, I should be telling you enough that you can get the general sense of it. And then some of you might even be bored of it. Who's heard of MapReduce? OK. Now we're starting to see more computer science out of this crowd. Because I don't think a lot of people with statistics background at this point have heard of MapReduce, but maybe they have. So Hadoop. What is Hadoop? I took this right off of Apache Hadoop, which is an open source implementation, one particular flavor of it, one of the more popular ones. And it says, Apache Hadoop software library is a framework that allows for the distributed processing of large data sets across clusters of computers using a simple programming model. So the idea is that you have a cluster of machines, like all these laptops. You string them together in a network, and you want some way to communicate work to them in a way where you don't have to think about the distribution. You just think about the work that you want to do. And that's the simple programming model. It's an open source implementation of MapReduce. That's one of 2 things that it really goes to its core. And then behind the MapReduce is a distributed file system called HDFS, which is optimized for MapReduce and makes MapReduce possible. Beyond all of that, out of this ecosystem have other technologies have sprung from it. We're not going to cover them today. These are database systems, tools for operating with databases built on Hadoop, those sorts of things. So Hadoop today, who's using it? So I took most of this information from a Cloudera conference on Hadoop last year. Some of it's gleaned from interviews out there in the world. The biggest user is Yahoo. They have 17 clusters at last report, 25,000 computers, 25,000 nodes, blades, whatever. And to say what they use it for is probably not fair. Because with that much processing, they use it definitely for more than one thing. They've got some web advertising research, and other researchers do whatever they need to do. Yahoo also contributes to the development of Hadoop. So they give back. They put back into the project. They recently merged their version of Hadoop back into Apache Hadoop. So it's available for everyone. And that's great. Facebook's another big player in Hadoop. They have a very large cluster, 2,000 nodes. I think they've experimented with a 4,000 node cluster, which is kind of the upper limit of what Hadoop can handle at the moment. And a lot of machines, tons of storage. They use it for daily processing of reports and research on the social graph, things that they're interested in. They also developed Hive. Hive is that database program that I mentioned before. So they've given back to the project too. And then the rest of these people, these brands maybe, you should recognize them all: AOL, GE, Bank of America, Twitter, eBay, Orbitz, LinkedIn. They're all using Hadoop for one thing or another. And Orbitz in particular has a data flow that most people would recognize if they've ever done any sort of analysis on data, any sort of analysis on the structure of data. Well, what they do is they get their web analytics logs from their websites about what you're doing. They put them on the HDFS. They put them into their database built over the HDFS Hive. But what they do then is they do queries. An individual researcher now interacts with that database. They query it. They bring that data back to R, and they do a data analysis. The problem with that is it's not really using Hadoop to its full power. It's not really distributing analysis and the kinds of work that you need to do for data analysis. It's using it as an enterprise-level database, and then the user queries it and comes back to R locally. They don't get any distributed processing. So what we're going to talk about today when we get to RIPE is how to do better than that. That's what we're interested in. We're interested in using the full potential of MapReduce for machine learning and analysis. I took the bottom quote from Hulu's website this week. So this is about a job listing. It said database developer, job listing, and under qualifications, it has experience with Hadoop development and administration a plus. So you guys don't want to be database developers probably, but this should mean something to you. All of this should mean something to you. This represents investment. They're investing in infrastructure. They're investing in people with these skills related to Hadoop. And for us as researchers, it asks us to take a closer look and see what's going on. What are they doing? What do they know? And that's what we do here. To you, by the way, this is the world you might be looking for a job in. So if you haven't heard of Hadoop, maybe you should. History of Hadoop. So the very top line is Nooch, which is an open source search engine. And Mike Caffarelli and Doug Cutting just had this idea: we want to make a search engine, we want to make it open source. But MapReduce and Hadoop really doesn't start there. It starts with Google. In 2003 and 2004, in about a 6-month period, I think, they first introduced their Google file system, which is going to be a predecessor to Hadoop's distributed file system, and they introduced MapReduce exactly like it exists in Hadoop. They didn't show the implementation, but they described the algorithm. So Doug Cutting and Mike Caffarelli see this, and it's a story of right place, right time, right ability, right motivation. They see this, and they immediately realize that this is what they need for Nooch. And they set about implementing Google's ideas in an open source framework. They call it Hadoop. It's a made-up name for, I think, one of those two children's toys. They write the first MapReduce. They put it on 20 nodes. They poured over this open source search engine. And they develop it a little bit to maturity, and then it gets Yahoo's attention. So Yahoo, in 2006, sees this, hires away key developers. I don't know if you can hire away from an open source project, but hires key developers. They put some of their grid computing on Hadoop, and then eventually the project gets contributed to Apache, which it nurtures open source projects. And then from there, it really starts taking off, because once it had Yahoo's attention, people started to notice. And then all these other players get involved. So this last quote is from 2011, and it's from Business Week. The best minds, this is from Jeff Hammerbarker. So Jeff Hammerbarker is a co-founder of Cloudera. Cloudera is a company dedicated to supporting Hadoop for the enterprise, for those entities that you saw before. And Jeff Hammerbarker graduated at the age of 23 with a PhD from Harvard, and he was hired away to Facebook to do research on the social graph as it related to Facebook and other things, and basically bring their research department into being. And he said in 2011, the best minds of my generation are thinking about how to make people click ads. That sucks. And I always thought this quote's poignant. The moment I saw it, I thought, this is poignant. But I think the people like Google who hired away these great minds, they had money, and Dr. Cleveland says the problems of data are universal. So they hired these people, they had them work on problems of data, and what they did, I think, was change computing forever. I really think that. I didn't think that before I got on board, before Dr. Cleveland, but after I saw Hadoop, MapReduce, I realized they've done something, and it's going to be a part of our lives for a very long time. Whoops, wrong way. So what is MapReduce? So I'm going to give you 3 different descriptions. I can only think of like 4 different ways to describe an algorithm. One's a verbal description, one's a pseudocode, one's a schematic, and one is to show you an actual implementation. I'm going to give you the verbal description, the pseudocode, and the schematic. And then it's that important. So MapReduce, I'm paraphrasing a great, a sort of unrelated paper, but they did a good job of describing it in a succinct way. A MapReduce is a job. You describe an input, a mapper, and a reducer. So you get data somewhere on your distributed file system. You describe a mapper and reduce an reducer, and originally those are implemented in Java. The input is a list of records consisting of key-value pairs. So you have a list, and you have a key on one side of it is basically a pairs list, and a value on the other side of it. And it doesn't have to be like primitives, a string to a number. It doesn't have to be that. It can be anything. A key can be a database, and a value could be a database. Key could be a number, and the value could be a planet. I don't care. It's some sort of data structure. And then a user-defined map. So we're saying user-defined map here because a lot of this is not handled by you as the user. A lot of this is infrastructure that you work with. But you do define a map, and you do define a reduce. And so the map gets a shot at the data, and it takes a shot at the data one key-value pair at a time. So you see one key-value pair, then you see the next key-value pair, and you see the next key-value pair as input to the map. And then you can output any sort of key values that you want. It doesn't have to be related to the input. It can switch them around. It can do some sort of analysis. One thing we output as values after we see key-value pairs, we have keys of between subset variables. We have values of within subset variables. And then our key values coming out of the map are plots. So it can be images. So those go to the reduce. The reduce takes a shot at the key value pairs coming out of the map. But what's different now is grouping. The map gets them in any sort of order. You can't depend on order. But the reduce gets one key in every value associated with that key. So you can bin things, you can count things, you can move things together. And then the output is whatever comes out of the reduce function that you've defined.
So is the key the same key?
No.
So you have a new key value pair that comes out?
You can, yeah, that's user defined. And depending on your algorithm, it may be the same thing. Maybe you just wanted to scrub out some of the data and remove some of the variables. Maybe you wanted to summarize them in some way, and it's still the same key because of that. Or maybe you're dividing up a document into words, and the keys are the individual words, and the values are the counts of the words in the document. And what's going to happen, by the way, if you're looking at the big picture, is to me, Dr. Cleveland and our group is setting out principles for selecting keys. That's really what we're talking about. So you can go through this. You go through into this framework. You have some task that you want to accomplish. And you can sort of just play with keys and values until you get the algorithm you want. But we're talking about principles for selecting keys. So pseudocode, it was at the bottom of the last page. This pseudocode kind of imagines that there is no distributed part of this. There's no all these laptops networked together. There's just one computer, one machine, and you're writing this algorithm. It says for each key value in input, call map with key value, and whatever it wants to output, put it in intermediate storage. Then group or sort. We actually sort, but you can think of it like group because depending on the algorithm you're writing, you might just want to get things together by key, or you might be taking advantage of the sort. You group or sort all the key values in intermediate storage by key. So after your map gets done with them, you put everything that has the same key together. And then for each unique key in intermediate storage, you call your reduce function with the key, the key that you're working on. And I'm saying values bracket key, meaning all the values associated with that key. So some sort of subsetting operation. And then that goes to the output. So that was the description. That was the pseudocode. And now let's talk about this little schematic I got. The most important part about this schematic is some of the vocabulary I'm introducing. Map task, reduce task, mapper, reducer. Map task is largely Hadoop. So Hadoop has this sort of process that it launches after you told it what data you want. It picks out a map task on a machine, assigns it data, and you've given it a mapper class. So it's going to go ahead and get the data. It's going to pull it from the HDFS for you. It's going to make an instance of your mapper class, and then it's going to give you a shot through an interface to do the work that you want to do. And then whatever you say coming out of the interface that you want to be output key value pairs ends up in local storage. And this bracket here, I'm really indicating multiple machines. So now we're starting to think about the distribution of these things. So there's multiple map tasks on multiple machines. Now when all the mappers are done, at least from our point of view, reduce tasks get launched and they get assigned keys to work on. Again, this is Hadoop. Again, you've given it a reducer class that you're interested in doing the work. And again, it goes ahead and pulls the keys from the local storage and hands them to your reducer. Whatever you output ends up on the HDFS. So an important part of this is these are not necessarily running on different machines. These could be running on the same machine. And we'll talk more about that in a minute. Is there any questions about that? MapReduce is pretty clear, right? Simple algorithm. I got 2 more graphs about it. So in this graph, I've pulled this from The Definitive Guide by Tom White. This is a pretty good book. And in this graph, they're emphasizing multiple reduced tasks, and they're also putting an emphasis on the sort and the shuffle. So the sort and the shuffle is how things get grouped together after they come out of the map. So we said that after they come out of the map, all the values for one key get put together. So you've got your view here. Split 0, split 1, split 2. Different chunks of the data get assigned to maps. This is both the task that Hadoop's defined and you doing your work. Outcome key value pairs. And the first thing that happens is they have to get sorted. And then essentially you're dealing with the merge operation. But these reduces get told what keys to work on from a taskmaster. And they request the copies that they need, and then they do a merge operation to get them all together. And you get that getting passed to your class or your work, and it ends up on the output. Pretty easy. Different view. This one, they're not emphasizing the sort. This comes from Pro Hadoop by Venner. They're not emphasizing the sort. They're emphasizing the keys and values that can come out of the map and reduce. In this view, again, some records get divided up for map task. And the one thing you should pay attention to here is this map task at the top has outputted a key 1 and a value 1. So it's got one one key, let's not talk about what they can be. We'll talk about what they can be after Dr. Cleveland gets some talking going. And this bottom one is of outputted key value 1, and this is a value 1 and value 0. So what needs to happen is these need to get together. This reduced task gets assigned to it. It makes that request. Key 1 ends up over here, and value 1 and value 0 ends up with it. And key 1 is nowhere else. It's only worked on here. It's only worked on by this reduced task. And so this reduced task will get to see all the values associated with this key. And then it will output some records. So that was MapReduce. I'm done talking about that until we talk about RIPE. Are there any questions? OK. So Hadoop distributed file system. Behind all this shuffling and moving things around and assigning work, you need a file system that will support it. So HDFS was built from the ground up and optimized for MapReduce. What it means to be optimized for MapReduce, and in particular, the kinds of data that we're seeing going forward, and we've currently saw in Dr. Cleveland's group, is it has to be optimized for large data, gigabytes easily, terabytes also easily. Streaming data access, you saw that MapReduce just needed to start at the top of a list and go to the bottom. So it's not about getting anywhere in a file that you want to go. It's about starting at one end and processing to the other end. Simple coherency model, cannot change a file without rewriting the entire file. That's changed a little bit. Facebook made it so that you could append to a file, but it's not write anywhere you want on the file. And that's because MapReduce doesn't need it. And if they added it, it would just slow things down or make things more complicated. And then replicate data across nodes at least 3 times. This is good for 2 reasons. This is good because you don't want to lose data. So you don't have RAID storage. You have actual replicates. But it's also good for the practicalities of distributed computing. So this is designed for MapReduce. A machine might be unresponsive. We don't know how much load we've put on it. And these machines are mapped. They run maps. They run reduces. They also run the distributed file systems. They're not 2 separate machines. They're one cluster that does all of this. So if your data's on it and it's busy, maybe that's not good. So just having replicates just makes everything a little more reliable. Not just in terms of keeping good copy of your data, but also makes it easy to work with. Locality. Okay, this deserves its own slide. Probably should have been by itself, because this is the big deal with Hadoop. Data and task nodes are the same machines. You move the work to the data. Moving data around a network is slow. It is slow, 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 slow. And if you're moving it further than just the rack in other racks, it's very slow. So it's not, once you start talking about moving data around just to accomplish your algorithm, you can stop talking about big O or whatever, because you've got slow in the way of big O. So, and what this means to us, because we want to work with R, is when we get down the RIPE, this moving work to the data is handled automatically for us. We don't think about it, and that's great. There's been some other approaches on distributed computing with R, and to my knowledge, they don't really automate this. They don't move tasks to where the data's at in the way that you don't. All right. In a way that you don't have to think about. But we get that. We get that with RIPE. We don't have to think about it, and that's awesome. So working with the HDFS is relatively easy. So who hasn't used Linux here? Nobody brave enough? Really? Really? So working with the HDFS is easy as far as manipulating your files, because they did it Linux-like as far as how they structured the commands. If you're in Linux, you type Hadoop, DFS, and then you type one of these commands over here: list, move, chmod, remove recursives, copy, and disk usage. all work exactly like you would think in Linux. You can talk to the file system in a way that you recognize. And that's handy. So here's a picture. This comes from the official website on Hadoop, distributed file system. So I just told you about easy, and now I'm going to tell you about hard. So the actual underlying structure is kind of complicated. You have one name node that every process has to talk to when they want to figure out where data is at. You have multiple data nodes spread out across racks if you're at the enterprise level. And you have replication and blocks all handled by the distributed file system. But my point for this slide is just this. Only one person in your group has to be aware of this. Only one person in your group really needs to understand this sort of administration. The rest of the people in your group, when you're working with Hadoop, just live back up here with these file manipulations. They don't think about this. They're aware of it, but it's not part of how they write algorithms. So I think that's everything I have on HDFS. Any questions about that? All right. So now I'm going to tell you about R. You already heard about R, and some of you already know about R. And the good news is I don't have a tremendous amount of material on it if you've already worked with it. So what is R? This, again, is from the official website. R is an integrated software suite of software facilities for data manipulation, calculation, and graphical display. And the developers of R specifically say they don't want to be known as data analysis software or whatever. It just so happens that they work with data and the kinds of tasks that you need to do with analysis easily because of the way they design the language. But this is what they're after: data manipulation, calculation, and graphical display. So it's based on S. It's a 1998 winner of the Association for Computing Machinery Software Systems Award. Dr. Cleveland already mentioned this. Big award. Other winners were Unix, text, Smalltalk, PostScript, TCP/IP, Remote Procedure Call, World Wide Web, TCL/TK, Java, Make, and if you've been around the Linux infrastructure, you've heard of most of these. So why did they give it an award? And they put this they quoted their own citation on their website. Will forever alter the way people analyze, visualize, and manipulate data. S is elegant, widely accepted, enduring software system with conceptual integrity thanks to the insight, taste, and effort of John Chambers. If I ever do something, can you describe me like that? Insight, taste. So it's had influence. It's still used today. That top quote is actually from 1999. This bottom quote, this is Daryl Paragabon. It's from 2009, and he's the former head of statistics research at AT&T Labs and currently at Google. He says, R allows statisticians to do very intricate and complicated analyses without knowing the blood and guts of computing systems. And we find that an interesting quote here in Dr. Cleveland's group, because that is what we're going to try to accomplish with RIPE. We want to know how to compute with Hadoop without knowing the blood and guts of Hadoop. So we have not changed the spirit of R at all. So proliferation, so just evidence of its success. Since 1999 when it was ported before that, but since then, there's 3 open source flavors of R on systems running Debian, basically Linux, Mac OS, Windows. Scripts generally work on all of those if they work on one, except for a few different packages that we won't talk about. There's been 3,049 contributed R packages. They range in 28 task views, and they run the gambit of everything you want to do with data, from Bayesian inference to survival analysis and time series, and machine learning and statistical learning. So some packages related to that. So it should be interesting to you as somebody interested in machine learning. Any questions about R? Let's talk about RipA. So at the very top, R plus Hadoop equals RipA. That's it right there. Hadoop, big technology. R, big technology. Until this moment, they have not worked together very well at all. But we want to change that with RipA. And Saptarshi, who invented, former student at Purdue, who invented RipA, really succeeded. And Dr. Cleveland had the good sense to support him and sponsor him and make it all possible. So we thank him for that. The goal of Hadoop is to join the power of, the goal of RipA is to join the power of Hadoop with the ease and flexibility of analysis in R. And our philosophy is to allow the researchers to do very intricate and complicated analysis without knowing the blood and guts of Hadoop. So we're echoing Darryl Paragabon there. We don't want to change that flavor. We want it to be about simplicity and the proliferation of packages that come with R and not about, oh, how do I get this to work in Hadoop? We don't want that. So the design has been to encapsulate Hadoop away from the R user so that the user can perform MapReduce-based analysis by working entirely with R data structures and entirely within the R environment. So originally, Hadoop was defined around Java classes. And we want to make it possible to pretend that Hadoop had been designed for R. So I'll talk you through a schematic of how this is all possible, since a lot of you said you've seen R before. So this blue box down at the bottom, this is you using R. You're in a terminal. You're on Windows. You're in a terminal, something that looks like a terminal on Windows. You have some sort of map expression, some sort of just whatever R code you want in the map. And you have some sort of reduce expression, whatever R code you want in the reduce. That idea of a function that takes inputs of map values and map keys and reduce values has not changed. You're in R, you load this RipA package, you go library RipA, and then you communicate your job to it. And then what immediately happens invisibly to you is RipA tells Hadoop about its classes. So it's written Java classes. It's written basically Java classes to organize the map and Java classes to organize the reduce. Communicates it to Hadoop via command, what classes to run, and Hadoop kicks off. So Hadoop, after being told what data you want to work with, assigns data to map task, and then it loads your RipA mapper Java class that you never see as the R user. The RipA mapper starts an R instance. It's not actually an R instance. Basically, it's compiled R with all the nuts and bolts gone from it. I mean, not nuts and bolts. All the stuff that you don't need to do this removed from it. It's basically just compiled against the code base. And then it also, something else is happening simultaneously. The RipA package has started a RipA server local to you where you're working with R. And this RipA mapper calls home and says, what is the map expression? Map expression gets communicated to the RipA mapper. The R instance is loaded with the map task data, and then the map expression gets a shot at it. And you never know any of this. And then that same picture where it gets put in local storage for the shuffle and sort happens. The reduce task gets assigned their keys. They get the data they need. The RipA reduce class gets instantaneous. It gets created. Starts the R instance, again calls home, says what's the user reduce expression. User reduce expression gets a shot at all these values in memory. So one thing I haven't mentioned here is at this point the data is R objects. The picture you get with your user map expression and user reduce expression is not just, oh, text files or, oh, whatever happens to be normally on a disk. You get actual R objects that have been persistent between sessions. They get serialized to the HDFS as keys and values. They get invisibly to you, they get put on the disk in a way that they come back the next time you do a MapReduce as R objects. So you live in an R world. So how that's possible, better get my mouse. here's our pseudocode picture again. Again, this picture hasn't changed. We have basically a map function and a reduce function. Only in R, calling functions has big overhead. It's slow. So this isn't implemented as calling a function. Here you are in your local instance. You say map equals an expression, and then your expression is whatever R code you want to run. And when this gets run, two lists are going to be put in memory. They're going to be a list of map keys and a list of map values that go with them. So you can do a sequence along map keys, or you can do a lapply along map values because they're a list. Here we're doing for I and sequence along map keys. That means every index in this list. And here we're going, oh, map keys give me the element at index I. Map values give me the element at index I. So we have now a key value pair. We do whatever work we want to do in R. And then this RH collect. Because we're not implementing this as a function, we have to have some way to communicate a return. And the way we communicate a return is through RH collect. We just say whatever key we want to go as output and whatever value we want to go as output. And we can call this as many times as we want. So in the spirit of MapReduce, there's no rules set in the algorithm about what you might omit from the map. There's no rules here about what you might omit from the map. And these are our objects. They can be data frames. They can be vectors. They can be lists themselves, anything you want. Then the reduce expression is also written in R. It's a little different. And it's a little different for an important reason. So the map only gets a key and a value, key and a value, key and a value. Hopefully, depending on how you implemented it, there's no memory issues there. I mean, yeah, you might want to store a bunch of them at once in memory, but there's nothing intrinsic in the algorithm that's going to run into a local machine problem where this is running. But reduce, you don't have that. So you could have one key, it could be one constant value, and you could have 1 billion values associated with it. There aren't any rules, remember. So you don't necessarily have the capacity or the desire to put them all in the memory at once. And you're going to see, when we get to examples, you're going to see examples where we might have the capacity, but we don't have the desire to work with them all at once. It's just inefficient. So, and this comes all the way from Java. This is how it works in Java too. You need a scheme. And the scheme is to be able to communicate how many reduce values I want at a time. And then I'm going to have a pre-interface, a reduce interface where it's actually like the function was running, and a post interface. And in this case, they're pieces of our R expression in R. And the pre is ran once per unique key. I kick it off. I say, what do I want to do before I see any values from this key? And then reduce is, you usually initiate some data structure there if you're going to use it. And reduce is how many values I wanted to see of the key at a time. It keeps getting ran over and over again until I see them all. But maybe I only want to see 1,000 at a time. And maybe there's 1 million of them, so this will run 1,000 times. And then the post says, after there are no more values for this key, what do I want to do? And depending on what we want to accomplish as the researcher, we might be calling this RH collect in the reduce, or we might be calling it in the reduce post after we've seen all the data. Any questions about that? To those of you that have used R, it's probably clear. To those that haven't, maybe you need to see more examples. So how does this happen? So I talked about, OK, you're in R down here. You've loaded some package with a library command. And then all of this happens basically invisible to you. That's made possible by a function. The crucial function for all of this is RHMR, stands for RIP A MapReduce. And this is where we communicate everything we want to communicate about the job. So we have an opportunity to tell it the map expression. We have an opportunity to tell it the reduce expression. And then there's a bunch of other stuff in here because I'm hiding some of the details from you. I'm hiding some of the issues like what's a combiner. A combiner is a reduce that runs on the map task so that you don't have to move as much data across the network. setup expressions, setup runs before any of the map starts happening or any of the reduce starts happening, and you also get an opportunity to clean up if you want. You need to communicate an output folder and input folder. That's crucial. Hadoop's very folder oriented, so you don't really input files. You input entire folders, and whatever's in there ends up as input. And then copy files, we'll talk about that maybe when we see an example in another day. Job name, it's always good to keep track of what you're working on. And that's that. After you communicate your map job to the RHMR, you call an execution function that basically just kicks off that whole scheme. And so what Dr. Cleveland's going to talk to you about is how we pick the keys and the values that we want to work with. And then maybe I'll talk to you again. I think that's what I had. Are there any questions? Yes?
So does the data that you are working on exist only in Hadoop, or can you pass local variables from your R program in does it capture locally scoped variables and pass them in?
It can. So there's two schemes to get stuff from your local R instance to your maps and reduces besides the map expressions and the reduce expressions. One is you could put there's a save format in R called the R data where you save out an R data. You can put those on the HDFS and load them if you tell RIPE that you want to do that. Or you can define variables that will end up in the environment that these tasks are run in. So you can define variables that end up in the environment, and you can get some really complicated stuff into R that way. So it's not just, oh, I want to pass a string or a number. You can serialize an object, serialize a list. It gets put into an environmental variable. You unserialize it at the map and reduce, and you can work with it. Yes?
I have a more general question. Can every statistical and machine learning problem be framed in the MapReduce framework, or a specific class of problems which can be abstracted as a?
Isn't that a paper-worthy question? That's a for all.
Well, maybe a specific scenario where you think that everything can be abstracted as in the MapReduce framework.
We're going to talk about how this tradition of between subset variables can be cast into a MapReduce setting, and analysis based upon sorts of divisions of data that have existed in R and data analysis for a long time. And so we're going to talk about that. As far as the entire breadth and scope of your question, I'd be interested in what you think because it's research. Anything else? Yes?
How do you compare right with Ricardo?
Excuse me?
How do you compare it with Ricardo, this technique? Ricardo is another technique to combine R with Hadoop. And I'm familiar with this, and this is new for me.
I've never worked with it. I've never worked with it. Dr. Cleveland, do you know anything about Ricardo?
I'm sorry, what's the name?
Ricardo.
Oh, no, we haven't, yeah, I've heard of it, but we haven't looked into that.
That sounds like something I need to know about. Thank you.
Isn't it slightly different? Somewhat similar. I just saw that we have a
It just definitely sounds like something I should know about if I'm going to be talking about this stuff. Thank you.
Let's make one thing clear. What we're doing is, at one level, this is not about algorithms for individual statistical machine learning procedures. Actually, you could think in those terms. Maybe it's I was going to say this later, but you have a question. Let me try to make this clear. We're parallelizing the data. And so when I take a subset, I can apply any method in the world. Well, let's say we're in R, you make a subset.
Oh.
Now I can apply anything in R to that subset.
Dr. Cleveland.
Yeah. Oh, okay. All right, so that's where we're going with this. Oops. Okay, so that's where that's where we're going this. So the real question is, how many data sets can we parallelize? That's the question. Now, it turns out, though, that you say, well, wait a second. That's a little bit limited, isn't it? Because I know if I'm going to, say, do linear least squares regression, we'll talk a little bit more about this. What do I need to do? Well, what I do actually is I take this, I have this matrix whose columns are numeric variables. And I'm going to take all the cross products of the p variables. And that's just going to be a sum. We're going to take all the inner products. So if I'm sitting there in this framework, I could actually implement within R, using all this infrastructure, I could implement a parallel external memory algorithm to do that, because it's just so easy. I just break it up into subsets. I'll do all the cross products for the subsets, then bring them all back, add them all up, and then take the proper inverse. So there is this opportunity for this other world, which is parallel, I'll call it parallel external memory algorithms. Or some people call them out-of-core algorithms. And there are a number of people working on this, trying to do this. Alex Gray at Georgia Tech, he says he's going to parallelize everything in machine learning. Okay. Now the question for that sort of an effort is, how many routines can we parallelize? Is everything parallelizable? And it opens a lot of tough questions. So I think the answer to that is, well, it's great. If you can do it, fantastic. And we'll grab it and we'll stick that in as a routine into R, and we'll use that.
I think the interesting question is what principles are guiding our selection of map values and reduced value. I mean, excuse me, map keys and reduced keys and reduced values.
Well, we actually might even want to use Hadoop and that infrastructure for doing the parallel external memory computation. I mean, it's like, it's right there, and of course it makes sense if you've got that environment to do it that way. But that's right, yeah, exactly. I mean, I think, you know, not everything is going to work. And even if it does, even if you say, no, I just proved the theorem yesterday that says that we can parallelize everything, it brings a lot of baggage with it. And remember, we've got thousands of routines to rewrite. So that's not going to happen in a short time. So we're sort of putting our money on parallelizing the data, and we'll see how it works out.
Yeah, the one thing I forgot to say that I'm kind of into is that you can sit down and you can translate algorithms to MapReduce. But when somebody's doing sort of an exploratory analysis, they need a more flexible relationship with the whole process in that. And so that's why I didn't really have a specific example of, oh, what do we do with MapReduce? Because what we do with MapReduce depends upon what we need to do with the data and the kind of work that we want to accomplish. And it has to be, it can't be days of development just to accomplish one thing, which is not what it is, the way we have it implemented. It has to be, oh, I have this direction I want to go, I'm going to go that direction.
All right, any questions about, okay. Any other questions about that issue? Let me just make one more comment. Reduce is the wrong word. I'm not the first person to say this, because it has an implication that when I do that reduce operation, I'm going to actually wind up with a smaller amount of information than I originally had in the input. But all the time, we routinely will use this infrastructure to create a whole new division where what comes out is not a reduction in information, but rather just about the same amount of information. And as a matter of fact, in principle, you know, that last step could create much more data than what came in. Now, we haven't had an application where we actually do that, but we do create new databases. So that reduce is really, it's like Pat Hanrahan at Stanford says, that really should be renamed and call it produce. So we can start calling it MapReduce. That's probably a better term, okay? All right, well, we're going to give you some, I mean, we've just been talking and very vague. So starting tomorrow, we're going to make this specific. We're going to put this in the context of the data, and you'll see map, key value pairs, how that is, you know, what does that mean on the data analysis side of the house? Okay? Any other questions or objections? Yeah. Yeah.
All the papers I've read about parallel computational, very few of them saying about, a lot of them saying about, is it possible to parallelize at all? But I'm interested in how well it is parallelizable. In order like speed up, for example, not like empirical result, but theoretical result. How, given the one algorithm, how well it will scale? We will talk about this, or what do you think about this?
Well, we'll make reference to it. I mean, our experience is it's been a miracle. We've gone from weeks to tens of minutes.
You're talking about generally all of them, so specific. Because some of them are better, like as you said, empirically parallelizable. Some of them are not. Some of them are almost impossible.
No, by definition, when we divide the data, it becomes, by definition, embarrassingly parallel.
But that's through new algorithms that you've developed that allow you to do recombining of the statistics that you're doing on subsets, right?
Tell you what, we're going to show you. Okay, we'll give you the example. We have one example. We're going to take you through that. So let's say what we've done generally. Actually, we have a whole bunch of examples, but we're going to take you through one. We can't take you through them all because we really have to get into the details so you can see exactly what it was that this did for us. So in that one example, so I won't go out on a limb here, one example, weeks to tens of minutes. Okay. All right, good. We got to quit because we got a break and we got next session. So see you tomorrow. Thanks.